Okay, hi everybody. May I ask to turn on your camera, please? As many as you can. Thank you. And hopefully, at some point, I see like more variety of you. So it's usual crowd that turn on their camera, and thanks to them. But hopefully, some other students also do that. I'm not sure why. At least most of you don't turn on your camera. Hopefully, if I put you as instructor, you will see it's very strange talking to the slide and not seeing you. So you will see why I'm asking you. Hopefully, beside that, which is strange, also it helps me to adjust the way I'm teaching, right? I mentioned that many times, but that would be useful. Okay, so a few things. Still, I'm waiting for the TA to tell me when he's done with grading. So today, unfortunately, I prefer not to go over the homework because I would prefer you to see the grades first, and then we have that session. It's going to be more effective to see that. So if he was able to finish grading before weekend, I may announce it to have this session over weekend, if you don't mind. If not, in the worst case, we can do it next Tuesday. Which one do you prefer? Do you have any preference overall? May I ask, like, your suggestion, if those who can put in the chat, how many of you would prefer over weekend or weekdays? I mean, weekends, like choosing sometimes in the afternoon, right? So most of us are awake. Okay, so it seems that weekend is fine with most of you, right? Okay, that's good. So so let's see. Depends on if he can finish that by tomorrow. We should have it sometimes over weekend, either Saturday or Sunday in the afternoon. If not, after usual lecture next Tuesday, so we can go over it.
Will you record that?
Yeah, absolutely.
Okay.
Definitely. I will record it, but it would be useful. Those of you who are interested, maybe asking question that changes the way I'm explaining things again. All right. Specifically for problem 2, which is somehow there are different way of doing that, the refactoring. So that is going to be useful, I guess. Is there any question you want to ask before we start? Okay, so let's continue.
There was 2 questions in chat at the top.
Oh, okay. Let me see. About the slide, sorry, I forget to put it there. I will do it as soon as possible. Sorry about that. The TA offered tutoring. I will ask him. Hopefully, he says yes. But yes, hopefully he can offer some tutoring. but if not, I will try to have like more of these informal sessions. I can explain more stuff beyond these lectures. I'm happy definitely to do that. I unfortunately, like usual things, as most of us as professor, we have very limited time. There are so many things happening, especially like this year. Started from last year. Several projects has started. I mentioned about these two NASA projects that we have. One NSF project, graduate students advising, all of this. So it's very time consuming, especially this time of unusual time because of the pandemic also changed things a lot. But as this is something that I want you to know, I really love teaching, especially this computer architecture class. I enjoyed a lot. And overall, I enjoy teaching undergrad classes, these basic classes, much more than graduate courses. I somehow get more energy when I'm teaching undergrad courses, so different from grad courses. So I enjoy more, especially computer architecture. So I don't mind spending like much more time than I supposed to do for this course. Hopefully going to be useful for you. Okay, let's continue discussion about microarchitecture. So we had this discussion that we have this contract ISA which specify the instructions and some other stuff that stays constant. So there would be no change for an ISA once it has been defined, right? And microarchitecture is implementation of the ISA. There could be several implementation of an ISA, and this is important for you to know. Like a very simple question in your exam, like whether we could have like 3 different implementation of an ISA. The answer is simple, yes, it's possible to have different implementation. Why is that? Because of different factors, right? Because of the trade-off space that we have talked about, right? So because of performance, and these design points that we have discussed several times. So we usually have different implementation of an ISA, different microarchitecture. So microarchitecture usually changes faster than ISA. So if you look around, we have like limited number of ISA, like x86, MIPS, LC3, which was not meant for traditional, for commercial purposes, right, for only teaching. And for x86, you see that so many different implementation over time, okay? Still is a dominant ISA out there. So it is important to know about this. And when we say ISA, we explain this involve, and we already discussed that in detail about instructions. So you know that instructions, opcode, addressing mode, data types, instruction type, registers, conditional codes, also memory, address space, addressability, stuff is part of the ISA that we have discussed, but there are also some few other items that we have not covered, and it's not, it is part of the ISA that programmer should be aware of, and typically these are more low-level part which system programmer cares more. System programmer meaning that those who write operating system, compilers, right? This system programmer care more about, like, for example, virtual memory management, interrupt, exception handling, access control, these privileges, thread management is very important, right? Power thermal management, multi-threading, all of these. So these are part of the ISA that we have not covered so far, and we will not. Technically, they are formally part of the ISA, because again, system programmer should be aware of it. System programmer again is that those who are above this ISA contract, right? So should know the whole details about the contract, so could write. But typically, normal programmers do not need to know about this, right? Except like few things like thread management, some of these in some special programming languages, which, for example, performance is important, okay? Like C, C++ stuff, and some programming languages, like some of these are not relevant at all because it's hidden to the programmer, and is managed in the layer below programming languages stuff, or by somehow a virtual machine. Like, for example, Java virtual machine manages some of these. Okay, you could think about it as a layer which sits somehow at the top of ISA, that manage some of these aspects of the ISA. And there are some design constraints about design constraint and also goals, performance goals, when it comes to implementation of an ISA. And for example, these topics that you see here are part of the macroarchitecture, you could say, relevant to the macroarchitecture that is hidden to the programmer, right? So for example, pipelining, out of order execution, clock gating, prefetching, voltage frequency, error correction, all of these is hidden from the programmers, and it is relevant only to the macroarchitecture, okay? And to be clear, we are not going to cover all of these topics. Some of important ones, for example, pipelining. And if we get enough time, hopefully out of order execution in detail, because it's important. And also memory access. Memory management is also a very important part of computer architecture. But I mean, all of these are important topics in computer architecture, and typically will be covered in advanced computer architecture in graduate level courses. So it's for this basic course, 200 level course, it's not necessary at this point. Right. Okay. And like, for example, these are some bunch of examples that you can get a sense what is part of the ISA, relevant to the ISA, what is relevant to the macro architecture, right? So for example, add instruction opcode. Is it part of the ISA, specified by the ISA, or it's relevant to the macro architecture? What do you think? Do you have any opinion? Could you put in the chat your answers? Yep. Yeah, we already discussed that. The opcode stuff is part of the instruction encoding and is part of the ISA, not relevant to the macro architecture. How about this? Bit serial adder or ripple carry adder? Different implementation of adder, right? Yeah, no, correct answer. It's part of the macro architecture. Again, you see alternative like bit serial adder or ripple carry adder. Two different implementation of an adder, which is used in add instruction, right? To implement the add instruction and some other instruction as well, right? Number of general purpose register is part of the ISA or macro architecture. ISA, yeah, we discussed that. So the general purpose registers are part of the ISA. So good answer, correct answer. Number of cycles to execute the mul instruction, multiplication instruction. Right, is part of the macro architecture. If you remember when we discussed the instruction, multiplication instruction, when you want to write a program, is it relevant to know the number of cycles? Not really. So as long as like this instruction is relevant to solve your problem, you can use it. Programmer doesn't need to know the number of cycles of instruction, so it's part of the ISA. Okay, and this distinction, like when you were asked to answer this in your exam, think like when I'm writing a assembly program, do I need to know this or not? And this distinction could help you to categorize this. Number of ports to the register file. What do you think? Is it part of ISA? Could you answer? What do you think? Why do you think no is part of the ISA?
I was thinking it was part of the ISA because it has to do directly with the register file. But now that I look at it again, number of ports might have to do with the microarchitecture if we're talking physical ports.
Yes, good explanation. That's right. Obviously, programmers should know the register, right? The general purpose register and register file, right? But how many ports it has? So it's part of the macro architecture, and it affects cost and efficiency, right? It's not relevant to the programmer, so it's part of the macro architecture, right? Good analysis. Whether or not a machine employs pipeline instruction execution, is it ISA or macro architecture? What do you think? Could you answer? It's fine if you answer incorrectly. Macro architecture. Yes, that's part of the macro architecture. Again, like for writing assembly, like you didn't need to know about pipelining, right? And we'll discuss about pipelining, right? Is one of the important topic in computer architecture and as a part of macro architecture, right? And it is essentially part of the macro architecture, not ISA. This distinction again is important. Is one of those easy questions could come in homework or exams. So make sure that you can identify the distinction and this, again, this thinking about like whether programmers should know or should be hidden from programmer help you to categorize these two. Okay. As we discussed, there are several design points that enable this trade-off. In both ISA, we discussed about trade-off space in the ISA extensively, if you remember, several times. The same is true for microarchitecture, especially is more important at the microarchitecture, the cost, performance, maximum power consumption, and thermal. This power consumption and thermal aspect is super important because it is possible to like make the CPU as fast as possible with some implementation, but your CPU will be boiled right away if you run the stuff on it. If you don't consider power consumption and thermal aspect of it. So it's not going to be a stable implementation. So it's very important to, one of those important design aspects of microarchitecture, energy consumption, obviously, especially for those CPUs or compute nodes that are for resource constraint devices, like such as our smartwatch, robots, right? Those battery connected devices. So if the energy consumption of this CPU is so high, then it's not going to be useful anymore, right? So we have these, one of the important design point for example, the CPU that sits in your watch or your mobile is this energy consumption. And some other aspect, for example, reliability, correctness, all of these stuff are running in some chemical things, chemical devices, and they are not typically reliable. So we have some techniques to make computation reliable by correcting these signals. By default, they are not reliable, so they could flip and could give you some incorrect signal, but there are methods for correcting these signals. There are methods, and there are like community work on this correctness aspect of this, and it's important part of the microarchitecture, and also security, safety stuff. So these are some important design points. And also we have the other aspect that that somehow has a relationship with this design space, right? So these items were design points, these cost, performance, but also these are enforced and somehow related to the application space as well, right? So we have so many different types of application with different demands, right? For example, scientific applications have totally different demand than like transactional databases, right? In scientific application, mostly you want the process to be fast. You load the data in memory and you do all of this crazy stuff in memory. In transaction-based application, like you typically access your disk, do some calculation, and again write to your persistent memory, and so on. So it's totally different type of application that has different demands, and needs to have different type of implementation when it comes to these domain-specific things, right? And we have domain-specific implementation, domain-specific architecture, essentially, as you are aware of, for example, due to these increase of machine learning-based systems, network applications, right? Embedded systems, media. So there are so many different applications. And essentially, like, again, we discussed about this, like being domain specific or general purpose. If you think about history, like at the very earliest stages, being general purpose was a dream. Like at the time, like there were design, implementation of a specific application that was made possible, but having a CPU, having a processing unit to enable to work for general purpose application was a dream. And when after so many successful years of using general purpose systems, general purpose computing, now you see that like the rise of, again, domain specific computing because of hitting the wall in general purpose CPUs, and the type of specific compute that we need for example, for machine learning is totally different from other type of, you know, compute that we need, for example, for web application. So this is also historical perspective. Okay. And also, like when it comes to trade-off, again, like ISA, microarchitecture, but also we have system and task level trade-off, okay? To divide things between hardware and software. And computer architecture is the science and art of making this appropriate trade-off at different layers. And it is why this course, computer architecture, is very important part of the curriculum for computer science, and why I like to teach this, why I enjoy this topic, because it's fundamental. It's one of those things, if you learn properly, you can do many things. I mean, again, I mentioned this to you, that maybe for writing systems in general, writing software, like most programmers do not know about computer architecture, right? See that, like even those who do not do computer science, they can write programs. I mean, some of them are super very good, and they know about this computer architecture stuff. I'm not making a general statement, but one thing that you can distinguish yourself as being a computer science major is that you see other programmers in other majors, they typically don't know about this stuff. And even like most of us, after we go to industry, we forget this stuff. We think that it's not important if like our job is like writing code, high-level code. But these are important, and this is why and how make you guys distinguish from other programmers if you know this well, because you can make trade-offs that others are not aware of. So be aware of this basically aspect, and try to learn this course as much as possible. And again, this distinction is important, so you can split the whole stack in different pieces, in 3 different specifically pieces. So you have the software part. We discussed problem, algorithm, programming languages, right? Which enforce the demand. So the demand really, if there is no application, there wouldn't be any hardware or architecture. There wouldn't be any ISA microarchitecture, right? So the demand comes from the problem, the top level, okay? These application side. The hardware also has some issues. Always there would be a need for having faster microarchitecture, and having some, like after several years, maybe a new ISA. So there would be some changes at the hardware level. Also from the user side, users also impose some demand and expect some capability from the other two, right? So distinguishing these three and knowing the dynamics between these three chunks is very important, right? So the user obviously should determine the problem. And also typically some of them use programming language to write program to solve this problem. And the user typically use the operating system, use virtual machine, this system layer that sits on top of the ISA, right? And this interconnection between software and hardware also, you're aware of it. So this dynamics is important to be aware of it. So all of these changes essentially what it enforces all of the changes at different paces, right? So again, I mentioned ISA might have some change from one ISA to another. One ISA is fixed, right, all the time. There might be some like version of the same ISA, but like the pace of change would be different at each layer, right? So microarchitecture has higher pace of change than the ISA. The programs, the software also has much higher change than all of these hardware aspects, right? Knowing these dynamics is very useful. And you can, all of this, you can think about it corresponding to like architecture in general, building architecture, that you have seen that the same building, the interface would be the same, the internals might change, the internal of the building, what is inside, the use case of the building might change over time, but the exterior, the design, the architecture is the same, right? So we can make this correspondence in like normal architecture as well, right? And there are so many examples that like the interface would remain the same, but the internals like also change. The use case of these buildings also changes over time. And there are so many analogy between computer architecture and architecture. Also, you should know that we have also software architecture, right? And maybe some of you have already taken, maybe not, but we have also software architecture, which is totally different topic than the computer architecture. You know that that course also is fantastic in a sense that it enables you to make trade-off when it comes to building a software, okay? To construct and build a software with different design aspect in mind, because software by itself, irrespective of the computation, irrespective of where you want to run the software, where you want to deploy the software. Again, the same thing: performance trade-off, reliability trade-off, usability trade-off, maintainability trade-off, and also some trade-off as design aspect. Trade-off aspect is different from software architecture to computer architecture, but mostly they are the same sort of trade-off aspect, which are important. Again, in software architecture, you want to make changes to the software itself, not only to the code that you write, but in the design of the software, right? So software also has different building blocks, has some interconnections, which could get very complicated at larger scale. Some of them, and you know that we have different also architectural style for software, right? So for example, we have component-based software architecture. We have service-oriented. Nowadays, like the popular software architectural style is microservices. Microservices architecture, if you search for it, is one of those super interesting and very popular architectural style these days that many software companies now migrated to microarchitecture, using microarchitecture style because this type of architecture is cloud native, so they can host their application into cloud and essentially build cloud native internet scale applications. So knowing about this trade-off that may happen at different layers for different purposes is again very important for you to understand. So I cannot emphasize more, but also distinguishing these trade-off spaces is very important to know about. Do you have any questions so far? All good? Okay, let's dive in. So far, we discussed what is microarchitecture. But now, we are going to discuss how we are going to go after it, how we are going to implement microarchitecture. Again, taking into consideration these design points, these different goals. So now we turn the focus more into like how these are done. Now that you know what it is and you can distinguish things from the ISA, now is time to focus on how this is done, really more toward the implementation and building stuff. Okay. And by implementation is that we want to have a design that again obeys this software hardware interface down the ISA, down the interface. You can do many things. You can violate things as long as you stick with the interface. Okay. And it's a combination of hardware and software. I mean, it doesn't need to necessarily be fully, this layer I'm talking about doesn't need to be necessarily hardware, could be a combination of hardware and software to enable that. Even though we know that like a full hardware-based implementation obviously it's going to be faster, but sometimes it makes sense to have a bit of software as well. Depends on, again, that affect these design points, right? So we could have, for example, a virtual ISA that is part of the microarchitecture that do some translation, right? So, for example, you could have a very complex ISA. You could have a layer that translate that ISA. Again, this layer is part of the microarchitecture. So imagine that you split the microarchitecture into like multiple layers. You have a translation like virtual ISA that does this translation to from complex to very simple, and then you implement this with the hardware, this simple ISA with the hardware, right? Or not necessarily need to be this layer, translation layer could be also hardware, right? But essentially you could have multiple layers even in the microarchitecture. This is what I'm saying. But here we mostly assume that we implement things with hardware, with these logic gates, essentially. But it's good for you to know that could be some multiple layers, could be also software involved here as well. Okay, some definition, important definition. And this definition is about what does processing and instruction mean. And it's very simple. In one Neumann model is nothing more than transforming one architectural state. And architectural state is the state that is visible to programmer to another architectural state, like from AS to AS prime. This is what is called a process instruction. Okay, this translation happened through process instruction that transform from one architectural state, transform the system from one architectural state to another architectural state after the instruction has been processed. So again, AS is the state before the instruction has been processed. AS prime, a state, architectural state after this instruction, this particular instruction at a time has been processed. And again, by one Neumann model, you should already know that there is one instruction at a time, right? One Neumann model assumes one instruction at a time. You cannot execute two instructions, okay? Like you remember we discussed last lecture about data flow, that it was possible to execute two or multiple instructions at a time. Do you remember that? So again, here, the assumption is that no, we stick to one Neumann model. For now, forget about data flow. So that was an example that it is possible to have another execution paradigm, that it is possible to execute multiple instructions. But for now, we assume that we go from one architectural state to another architectural state by executing only one instruction at a time. So we stick to the great one Neumann model. And these are two properties, very important properties of one Neumann model that you already aware of. So this process instruction step, again, is important. It defines somehow, you can think about it even as a finite state machine, right? So you can consider a finite state machine where a state determines the programmer visible state of the machine. Again, important. There could be some state hidden to the programmer. Some part of the machine could be hidden from programmer for some purposes. So there could be some states, but here states programmer visible state. This distinction is very important. You realize why it is important for a specific type of macro architecture that enable more performant type of implementation. And we will get there soon. And next state logic is basically the same as instruction execution specification. From the ISA point of view, there's no intermediate states, right? So ISA, only machine goes from AS to AS prime during the instruction execution. But down there, again, there could be some multiple states going on without being exposed to the programmer. The same that I mentioned. So so basically we could have two choices, right? One choice is that we go from AS to AS prime that transform basically does this transformation through one cycle, one single cycle, clock cycle, or basically in between there could be some state transformation happening. Choice two, again, these intermediate states are not visible to the programmer, and you see that this AS would remain AS throughout, right? And would be transformed to AS prime once the execution has happened, and these intermediate states are not visible to the programmer at all. So programmer thinks that all the time from here to here, I was in the same state. But really down in the macro architecture, this choice two could be multiple state transformation going on. Yes, Ross.
So is this like the level at which we like look at whether it's like a Turing machine or not? Like, is this like, would this sort of stuff be helpful for us to look at that?
Turing machine?
Yeah.
Maybe, but you don't need to. But I presume, I mean, the only thing that you should know at this point is like what is a finite state machine, which all of us know, right?
Yeah.
But no, it's always great to to read and know more about Turing machine. But for now, probably you don't need that for understanding these material, right?
Gotcha. Okay. Thanks.
Sure. So this choice one and choice two, distinguishing these two are important because it is how we can distinguish between single cycle or multiple cycle kind of processing. And again, this affect performance greatly. And we will discuss in detail why. We will make that very clear of how how it affects performance, this distinction going from one architectural state to another architectural state, either in one cycle or multiple cycles, multiple clock cycles, right? So in single cycle processing engine, again, each instruction, the assumption is that each instruction take only one cycle to execute, okay? And we use combinational logic to implement the instruction execution. And there is no intermediate state update in between, okay? Once the processing of the instruction has been finished in one clock cycle, the machine would be transformed to AS prime, the new architectural state of the system. None of you asked what is architectural state. Do you have any idea? I mean, we discussed this back in several lectures before, but can you remember?
Is this like a, well, I don't know. We talked about this kind of a while ago, but it would be like a flip-flop, because I remember when we talked about flip-flops, obviously like with the clock cycles, that helps us keep track of the state of the flip-flop, which is instrumental to the entire state, like how our machine runs, basically.
Right.
Is it like a finite state machine? That was my guess.
Finite state machine. I mean, all of these, I mean, flip-flop, finite state machine are part of these like implementation of this, but architectural state essentially have very clear definition is what is exposed to the programmer, right? And you have written couple of programs assembly so far, right? For your homework, for example, like what did you need to know? These stuff, right? So registers, memory, program counter, okay? These are part of the system that is exposed to the programmer and determine the state of the system, right? So basically, these are programmable, programmer visible architectural state. The memory, you see that as an array of memory cells. We discussed about it. Register, a bunch of, again, a special type of memory, faster implemented in different way than this memory, right? But again, you can store data in there. You can read from it. You can do things with it. And they have a special name, also part of the ISA. And the program counter, which specify the memory address of the current instruction, where currently PCEs determine basically the current instruction that is being executed. So these three part is the architectural state of the system. And like, think about it, is very intuitive for you now. Why, like, from moving from AS architectural state to AS prime happening by executing one instruction, right? So imagine now we have a specific state, and now we are being one instruction is being executed, right? So for example, say add, right? What it happens is that by executing this instruction, either of these or multiple of these is going to be changed, right? So for example, by executing the add instruction, can you tell me what part of this architecture state is going to be changed? Do you remember the add instruction?
Changing the value of a register.
Okay. So the register is going to be changed? Is that the only thing?
Sorry?
Is that the only thing that is going to be changed?
Memory.
Why memory?
Because you're changing the value of what's stored in that register, and that has to be updated in memory.
But is it part of the add instruction? Or if you remember, add, does it need to change the memory as well?
I mean, you just have those three registers as the argument.
Yeah, so you have only three, and there is no memory in part of this instruction, right? So
yeah,
the assumption is that it doesn't change the memory, okay? Only change the content of one register, right?
Right.
Is the destination register, right? So after, like before executing add, we have some stuff everywhere. After executing one add, definitely we know that one register that is specified in this instruction, for example, say S1, okay, in MIPS as a destination. After executing add, we definitely know S1 is going to be changed, right? So we definitely know that S1 is going to be changed, but not other, right? Not other. After this add, we know that only one register is going to be changed. Other registers should be no change in that. Memory should be no change in that, right? Like at this point in the machine, nothing else is going on. It's like one instruction at a time. Nothing else is going on. After executing the add, the only thing that we know should change is this S1, not memory. Is there anything else that needs to be changed?
The program counter to go to the next instruction.
Exactly. So this was part of instruction as well. So program counter moved to the next one. And next one was where? Moving like up, how many bytes? In MIPS, 4 bytes, right? So one word, 4 bytes. So incrementing program counter by 4, whatever it was in program counter, again, program counter, think about it as a register, a special register, 32 bits, like you add whatever it was in the program counter, after executing add, it will be added by 4, right? So add only the target destination register and program counter change. Is it always the case? Not really. It depends on particular instruction, right? So imagine like other instruction, like say no op instruction, right? In no op instruction, what architectural state is going to change? Do you know?
Just the program counter. We just move on to the next instruction.
Excellent, right? Just the program counter. The program counter, again, you add 4 to it. Nothing in registers and memory should change, right? So depending on the particular instruction, and we know that we have a bunch of instruction related to memory, right? Write word, okay? like after writing a word, after writing the word in memory, we know that after this instruction, memory will change, register, no change, right? Program counter changes, okay? In jump, what is going to be changed? Only program counter, not by 4, but what is specified in the jump, right? So essentially, this architectural transformation happens like after each instruction, no matter what, right? So there would be changes after each instruction. The scope of change really depends on the instruction, what is a specified instruction. And it is precise, right? So after executing instruction, we know exactly what part of the architectural state has changed, right? So if somebody asks you, what is architectural state? Know this definition, right? It's register, memory, program counter, okay? And if you forgot about this, again, think about the instruction. Like when I have add, like I only change the register. Okay, register should be part of the architectural state. Also, PC change, so PC also is part of the architectural state. And I have a bunch of like memory and structure, right? So you can like remember like these 3 were part of the architectural state and nothing else, right? So these are the only things that are visible to the programmer. Nothing else in terms of the state. Okay, so please be aware of this and know about this distinction. Okay. Hopefully now it's clear for you. And because also this definition is important to distinguish between single cycle machine and also multi-cycle machines. In single cycle machines, each instruction takes a single clock cycle to execute. No matter whether this instruction is add or multiplication or division or no op or whatever, right? No matter what instruction it is, it should take only single clock cycle, okay? And all state updates made at the end of instruction execution, okay? Big advantage is that I mean, big disadvantage. I was confused why it is big advantage. Big disadvantage is that the slowest instruction determines the cycle time, right? So for example, like we know that no op is doing nothing, so should be executed like very quickly, like only like you need to increment the program counter, so it's very quick. But some other instruction may take longer, specifically those instructions that access memory, like writing to memory is way slower than like manipulating a register. Memory is like way slower, order of magnitude slower than manipulating things in register file. So this is why like a big disadvantage is that like then our clock cycle could be slow as the memory manipulation instructions. So no op, even though essentially it's very quick, but if you have a no op, if we add a no op to a program, like it takes as time as having access to the memory, right? So if you have a program that have like 10 no-op, and if you have a program that have 10 memory access, both of them like take the same time. It shouldn't be the case. Like no-op should be executed a lot faster in total. So that's a big advantage. Disadvantage in multi-cycle machine, you don't need to obey that instruction processing. You break it into multiple stages, and these stages determine the clock cycle. So and there could be some state updates during instruction execution, and these state updates, again, not visible to programmers. Again, this was option 2 that we discussed like a few slides back. They are not visible to programmer, but like we could have some state updates down there at the microarchitecture level. And the slowest stage determine the clock, the cycle time. Yes, Raf.
So what I thought I heard you say about single cycle machines was that each instruction takes one clock cycle to execute, from no-op to multiplication.
Right.
Could you explain, if it's not too complicated, if it doesn't take us too long, why that is? That doesn't make sense on a general rule of thumb level, that multiplying like two 32-bit numbers is exactly as quick as doing nothing.
Good question. Let me explain it this way. So we know that cycle, like when we design a machine, like you could not have like multiple clock cycle time, right? So when you decide that cycle time is like 2 microseconds, right? Then your cycle time is 2 microseconds, okay? So it's fixed, right? So if that's the case, and if you have to stick to the case that all instruction should take 1 cycle time, right? Then you have no choice rather than designing in a way that this cycle time will be determined by the slowest, and those who can finish faster should wait, right?
So in this example, 32-bit multiplication, let's imagine that's the longest executable.
Okay.
Then everything faster just pauses when it finishes until the 2 microsecond has happened?
Right.
Okay. Gotcha.
So what is your question again?
Oh, just understanding that.
Yeah, exactly.
Making sure I'm with you.
But
everything faster is paused, but the slowest is the...
needs to wait until, because like it has to wait until, so the program could move toward the next instruction after one clock cycle, right? So if one thing finish faster than 1 clock cycle, it has to wait, right? So I finish, I have to wait until clock cycle finish, so next instruction can get executed. But I cannot design it in a way that, if I want to stick with a single cycle, I cannot design it in a way that the clock cycle will be determined by the faster, because like if it is faster, then like how I manage it, the division is much slower than like multiplication typically, right? So like I cannot design a machine that like if I consider like multiplication as a determinant of clock cycle, I cannot finish this division job in 2 microseconds. Like is you know, so we should base our longest execution time based on the slowest task, right? Because we should make sure that in each clock cycle, all instructions can get executed and can change the architectural state at the right time. Otherwise, like our whatever program that I write is nonsense, right? So in one clock cycle, like if division cannot be done, like if I move to the next instruction, wait, is division has not been done yet, right? So your program is not semantically correct, right? So that's the case. But in multi-cycle, you don't need to stick with this. So you could have multiple stages in between your architectural state changes from AS to AS prime. In between, while these changes, these state transitions are not really visible to the programmer, and the cycle time determines by the slowest stage in this case, not the slowest instruction, which is different. So typically each instruction can have different states, right? And how stages and how to split these into multiple stages is how determine the clock cycle and how fast the processor is. I hope this is clear. Let me see. Yes, let's stop here. Next time we are going to again this basic definition is used, and these are important because next we are going to go into much detail about this cycle and how things get implemented. So things become more detailed, and we go into the detail of implementation. Yes, Ross?
Do we have a tentative exam date? If not, it's fine. I was just wondering if you had something floating around your head, maybe a range or like around.
For midterm, you mean, right?
Midterm, sorry, midterm. Yep.
Yes, it's going to be this month, but I will try to give you a date as soon as possible. Bailey, I'm waiting because I want you to have more homework. So it really depends on this. To see more homework would be useful, so you have less stress what you expect to see in the midterm.
Right.
Yeah. So yeah, I will announce it soon. And again, I don't want you guys to be worried about the exam at all. So as long as you you learned about the lectures and you did your homework and stuff, you should be all right. So there's no stress things going on. So do you have any other question?
Yeah, I have a question.
Yeah.
Would there be some sort of like review packet for the exam?
Review packet. Maybe if that is going to be helpful for you, maybe, but review packet would be the same. I mean, the whole packet of homework that you see, right? Let me see what I can do, but I may give you some examples and stuff. Yes, Ross.
I also had a question about the midterm. the homework will of course prepare us for the material on the midterm, but will the midterm, do you know yet if the midterm will be taking the form of more of like a take-home project, like the most recent homework assignment, or more of a traditional exam with questions and a time period and such?
Good question. So definitely it would be a combination of questions and like programming stuff. So is of that sort. In terms of time limited, is time limited. But due to these, all of this situation, the time is not like, for example, 1 or 2 hours, is a little bit more, but it's not like several days, right? I haven't decided yet how much time I give you guys, but would be enough and much more than normal exam that you sit in a class and you have to answer the questions. To have like flexibility for all situations that you have. I try to give you as much as time as possible, so you have enough time and you can do it based on like your flexibility. Again, like I would give some, like, say, for example, I would say this exam you should typically spend like 2 hours. I may give you like 24 hours, but you do it in 2 hours, right? This is my suggestion, but I give you this flexibility.
Thank you.
Sure.
Thank you, Professor, for the lecture today.
Sure. Thank you.